Okay, so like I just said, we're just going to review the stuff that we've done since leaving school. So that's what your homework is going to be on. So I'm going to start with a proof. So proving 2 plus cotangent squared plus tangent squared over secant squared cosecant squared equals 1. Again, don't forget proofs require really good structure. And also, just as a reminder, don't hesitate shouting out over your microphone if you have questions or need me to stop for a second. I'm going to ignore the chat. I minimize the entire Chrome window. Can someone just shout out and make sure you can see my screen okay with the map?
Yeah, I can.
Okay, thanks. So I'm going to start this proof. Don't forget, a proof always starts with what you're given on the left-hand side. So 2 plus cotangent squared plus tangent squared over secant squared cosecant squared. And also don't forget, proofs mean you have lots of different roads to travel to get to the same place. So just because I may do something in one direction doesn't mean you can't do something else. So for me, what I think of immediately is when I have squareds on things, I think of the Pythagorean identities. And cosine squared plus sine squared is 1. But I also know the secondary identities involve cotangent and tangent. So I'm going to replace in the numerator, instead of that 2, I'm going to break that 2 into two ones being added, because in the secondary Pythagorean identities, we have 1 plus tangent squared and 1 plus cotangent squared. So when I broke up that 2, I know I'll be able to simplify that numerator using those identities. Another strategy would have been to take everything and turn them in terms of sines and cosines only, and then start simplifying things by combining fractions together and simplifying that way. So that would be another strategy. So here I know that 1 plus cotangent squared together is a cosecant squared, and I know that 1 plus tangent squared is secant squared. So in my numerator now, I'm going to replace those things. So 1 plus tangent squared is secant squared, so I'm going to replace that green stuff combined, plus the red stuff combined, 1 plus cotangent squared is cosecant squared. My denominator I'm going to leave the way it was. So all I've done so far is simplify and rewrite with Pythagorean identities. Now that I have this, I see addition in the numerator, multiplication in the denominator, which means I'm going to separate this stuff out into two fractions. So I have secant squared of x over that denominator plus the other fraction is the cosecant squared over that same denominator. All I've done is separate the fraction. And now I can cancel things in common. So in that first fraction, secant squared cancels on top and bottom, which leaves me with 1 over cosecant squared. And in the second fraction, cosecant squared cancels on top and bottom, leaving me with 1 over secant squared. And now each of these things is a reciprocal identity for sine and cosine. So 1 over cosecant squared is simply the reciprocal identity for sine squared. And 1 over secant squared is the reciprocal identity for cosine squared. And now that we have sine squared plus cosine squared, that's the primary Pythagorean identity, which we know is equal to 1. And that's what we were trying to prove from the beginning. So I know my proof is done, so I'm going to add that QED. So again, the structure, everything is aligned vertically. I started with my left-hand side up top. I ended with my right-hand side that I wanted on the bottom. Everything is in logical order. Any questions here?
Yeah, I have a question.
Yep.
So I see that if we had like 1 plus like tangent, we'd get like, um, is that cosecant?
Well, 1 plus tangent squared is
Oh
secant
yeah.
squared. But they have to
Well,
be squareds, otherwise it's not true.
Right, but what if we had something like 2 plus like tangent squared, like something greater than 1 being
Yeah,
added
that wouldn't work.
onto trigonomic like function?
Yeah, that wouldn't work. So it has to be a one. So just like to start with, if I had 2 plus cotangent squared only, I wouldn't be able to turn that into cosecant squared. But the 2 I could split up into the 1 plus 1, and then with one of those ones plus cotangent squared, that would become cosecant squared.
Mm. All right.
Cool. And my computer is not freaking out on me. The fan isn't going. So far so good, although I still have a suspicion that this isn't actually recording my math screen. It's just recording the meat. But hopefully Mickey's right and I'm wrong about that. So I'm going to move on. Now, this next problem, I put one of these on your homework. It's just a lot less intimidating to look at. So it's simplifying an expression until you get something that I've asked you to get. It's basically writing a proof, but without you being asked to prove something. So at the end of what I'm doing, I'm not going to put a QED. But other than that, it's basically the same thing I was just doing as far as structure goes. So I need to show that simplifying this whole mess of stuff yields an integer, meaning the final thing I need to end up with needs to be a single number with no trigonometry involved. So unless I end with something like that, I won't be done. Okay, so again, I'm going to kind of start this as if it was a proof with structure. So I'm going to rewrite what I have to start with. And again, I'm going to just rewrite using identities that I know, algebra that I know, arithmetic that I know, until hopefully I end up with just a solitary number. So first thing I see is in my denominator inside, I have sine 2x. I could use the double angle formula for that. So let me rewrite, and everything else stays the way it is. So double angle formula for sine is that 2 sine of x should equal 2 times sine of 2x equals 2 times the sine of x cosine of x. All I've done is replace with the sine double angle formula. Now with that expression in parentheses, cosine of x divided by cosine of x would cancel each other. And the 2 divided by the 2 would also cancel each other. So I'm just going to kind of show that. It's not a proof, so I'm not worried about showing canceling inside. With a proof, you wouldn't want to kind of take out stuff in your work. So that stuff cancels. Up top, that leaves me with a 1. So sometimes some of you leave this kind of thing with a sine of x. Don't forget, there's a 1 upstairs in that numerator, not nothing. Okay, so now I have 3 times negative cotangent squared plus 1 over sine. That stuff is still being squared. Now I'll actually just go ahead and square that 1 over sine of x, or if I want, I can use the reciprocal identity for 1 over sine. 1 over sine is cosecant, so let me actually go ahead and do that first. Everything else stays the same. So I've used the reciprocal identity. Still would have to square. So now I'll go ahead and square that cosecant. Cosecant squared of x now. So here now I'm at a juncture where I'm recognizing things are squared. So my mind immediately goes to Pythagorean identities. And thinking about the Pythagorean identity that involves cotangent and cosecant, I'm just going to write that on the side. As with the previous page, we knew that 1 plus cotangent squared equals cosecant squared. So what I have in the actual problem I'm doing is just a reordered version of what I wrote in green. So here, if I subtract cotangent squared on both sides of that Pythagorean identity, I would have a 1 left over on the left-hand side. And this stuff, cosecant squared minus cotangent squared, is exactly what I have in blue. It's just written the other way around with the negative cotangent squared in front. So if I need to show that explicitly, I'll go ahead and do that. So I'm just rewriting the order with which these were written in. So instead of a plus b, I just wrote b plus a. And now this stuff is what I have in blue inside the brackets. And that stuff is just supposed to equal the 1 that I have. So now all I have is 3 times 1, and 3 times 1 is just 3. And that is an integer, so I know I'm done. And again, I'm not putting a QED because this wasn't a proof. So it's not like I was supposed to be proving that the stuff I started with equals 3. All I've done is turned it into a form that I was asked to find, basically. Any questions here?
So when you expanded that denominator of sine times 2 of x, 2x,
Sine 2x.
how did you get a cosine in there?
So that's the double angle formula. So you would have to go back and look in your notes when we did double angles. Double angle identity for sine 2x was 2 sine x cosine x. So that's just like the definition of what sine 2x means. And that would be on your formula page. Also, the other thing you guys probably noticed from what I sent you guys was I put together a formula sheet with all of the identities that we went over and all of the formulas. If we were having a quiz, which essentially the mixed review I sent you guys is basically the quiz I would have given you guys. So if you had a quiz, that reference sheet was what I was going to give you guys to study for that quiz. But again, you could have made your own reference sheet, but that's just where everything is listed in case it's helpful. So as you're doing your homework, you can use that reference page, obviously. So moving on, evaluating tangent of 17 pi over 12. So moving past proofs, now we're getting into sum and difference formulas. So this is the kind of problem where on the side, I probably would note to myself a way to get 17 pi over 12 using special angles that we know. And there are lots of combinations that'll do it. Essentially, you're looking for things to either add or subtract to give you 17 pi over 12. And you're hoping that your fractions that you come up with can reduce so that instead of having a denominator of 12, you have something with a special angle like a 2, a 3, a 4, or a 6, or a whole interval full of pi. For me, what I think of first is 15 plus 2 would give me 17. So 15 pi over 12 plus 2 pi over 12. And I chose 15 and 2 because 15 and 12 share a common factor. So I'll be able to reduce that. And 2 and 12 share a common factor. So I'll be able to reduce that. So 15 pi over 12, if I divide top and bottom by 3, would give me 5 pi over 4, which is one of our special angles. And 2 pi over 12, reducing that would give me pi over 6, which is also a special angle. So those are the two angles I'm going to use to give my 17 pi over 12. So setting up my problem, tangent of 17 pi over 12. By definition, tangent's quotient identity is sine over cosine. So I'm going to replace that with the sine of 17 pi over 12 divided by the cosine of 17 pi over 12. And now again, instead of 17 pi over 12, I'm going to use 5 pi over 4 and pi over 6, which add up to give me 17 pi over 12. And again, there are other combinations that you might have been able to come up with. The final answer should still match at the end of the day. And now I'm set up to use the sine sum formula and the cosine sum formula. So again, you'd have to look back in your notes or the reference sheet. In the numerator, the sine sum formula says take the sine of the first angle times the cosine of the second angle. Keep the addition symbol the same. And then we're adding the cosine of the first angle times the sine of the second angle. So that's my sine sum formula in my numerator. Denominator, I'm going to use the cosine sum formula, which says the cosine of the first angle times the cosine of the second angle. Change the operation in the middle. So instead of plus, it's a minus, according to the formula. And then multiply the two sines together. So that's me using the sum formulas for sine and cosine. Don't forget, in this setup now, you can't cancel things that are in common because of that addition and subtraction in the middle. We can, however, evaluate all of these trigonometric expressions using our unit circle. So sine of 5 pi over 4 is negative root 2 over 2. Cosine of pi over 6 is a positive root 3 over 2. Cosine of 5 pi over 4 is another negative root 2 over 2. And sine of pi over 6 is 1/2. So that's the numerator. Denominator, I have those same expressions, but in a different order. So negative root 2 over 2 times root 3 over 2 minus negative root 2 over 2 times 1/2. Again, we still can't cancel things because of the plus and minus, but I can multiply my fractions together. So negative root 2 over 2 times positive root 3 over 2 would give me a negative root 6 over 4 plus, but then a negative times positive would give me a minus. So adding a negative just means I can put a minus. Root 2 over 2 times 1/2 is root 2 over 2. Oh, sorry, root 2 over 4. Same thing on the bottom, negative root 6 over 4. But the double negative on the bottom means I'm going to have plus root 2 over 4. My dog's barking in the other room. I don't know if you can hear that, though. Bringing that stuff up top here. Still can't cancel because of the subtraction and the addition in the middle. But these fractions have common denominators. So on the numerator, negative root 6 over 4 minus root 2 over 4 just means I can put them together as negative root 6 minus root 2 all over 4, dividing by, in the denominator, negative root 6 plus root 2 all over 4. Now I've gotten rid of the addition and subtraction, so I can start dividing these fractions. Since they have the same denominator, I'm just going to use my shortcut of canceling those denominators. So now I have negative root 6 minus root 2 divided by negative root 6 plus root 2. I'm back in a position of having addition and subtraction, so I can't cancel, but I have radicals in my denominator, which means we should be rationalizing our denominator. And that means, what should I multiply top and bottom by here? Anyone on the mic?
You'd multiply it by the reciprocal.
Not quite the
of the denominator.
The conjugate of the denominator.
That, yeah.
So the conjugate is negative root 6 minus root 2. So keep everything the same except for that middle operator. So instead of plus, it's now going to be a minus. And that should get rid of our radical in our denominator. So foiling here, in the numerator, negative root 6 times negative root 6 gives me a positive 6. Negative root 6 minus root 2 gives me a negative root 12. Another negative root 2 times negative root 6 gives me another negative root 12. And a negative root 2 times negative root 2 gives me a positive 2. So that's my numerator. Denominator should simplify without a radical. Let's make sure that happens. Negative root 6 times negative root 6 is a positive 6. Negative root 6 times negative root 2 gives me a positive root 12. The inner terms, root 2 times negative root 6 gives me a negative root 12. So there's the things that cancel. And a positive root 2 times a negative root 2 gives me a negative 2. So canceling those middle terms in the denominator. Up top in the numerator, 6 plus the 2 on the end give me an 8. Negative root 12 minus another negative root 12 gives me 2 of those root 12s negatively. Denominator 6 minus 2 is just a 4. Here I could simplify by dividing everything by 2, or I could simplify the root 12 first. Doesn't really matter which direction you want to go in. I'm going to go ahead and simplify the root 12 first. So the square root of 12 is equal to the square root of 4 times the square root of 3. Still all divided by 4. And then that square root of 4 is just a 2. And that 2 times the 2 in front of it would give a 4. So I'm kind of going to skip a step since I'm running out of room and just write negative 4 root 3 over that 4. And now I'll reduce the fraction by dividing everything by 4. So canceling 4 from all three terms would leave me with a 2, a minus 1 root 3, but that just means root 3, all over 1. But 2 minus root 3 over 1 is just 2 minus root 3. So my final answer is 2 minus root 3. So again, from the beginning, tangent, sine over cosine. I figured out 2 special angles from our unit circle that combine to give 17 pi over 12. And then I used the sine sum formula and the cosine sum formula to expand. I evaluated all of those expressions using my unit circle. And then from there, it was just like an algebra 2 kind of situation where all we're doing now is multiplying fractions, adding fractions, subtracting fractions, dividing fractions, until we got to the place where we needed to rationalize the denominator, which is another algebra 2 topic. And then doing that just means simplifying what's left. Any questions here? Okay, and again, I will either redo this or send the recording that hopefully is working when we're done. And I'll send these notes too, but don't forget, you have class notes on all of this stuff when we learn the isolated topics rather than just doing them all at once today. So you can always use any of those other class notes as well. So sticking with sum and difference formulas, solving a trigonometric equation using sum and difference formulas, let's review that. First thing it looks like I would want to do here is get rid of all the 2's by dividing everything by 2. You don't have to do that. I think it makes life simpler to get rid of the common factor. So now I just have the cosine of beta plus pi over 4 minus the cosine of beta minus pi over 4 equals a 1. Now is where I'll expand using my sum formula for cosine and my subtraction formula for cosine. Don't forget, because my middle term is a minus, when I expand the second one, I want to put that in brackets or parentheses because that negative in the middle needs to distribute to both of the things that's going to result when I expand. If it was a plus in the middle, that wouldn't be so important, but don't forget that's a really critical step when we have minus. So using the sum formula for the first stuff, I have cosine of beta times cosine of pi over 4. Instead of plus, this formula for cosine is switch the symbol to minus, and then sine of the beta times sine of the pi over 4. So this was me expanding just the first cosine of beta plus pi over 4. Now we have the main subtraction. I'm going to open brackets because it's going to matter to distribute the negative. For the second cosine term, I'm going to use cosine difference formula. So cosine of beta times cosine of pi over 4. Switching the negative symbol to a positive as the formula dictates, and then the 2 signs multiplied. Still equal to 1. Now I would have to distribute that negative to both of those terms I got in the brackets. So the negative cosine beta cosine pi over 4, that will end up canceling with the cosine beta cosine pi over 4 in the front. So I'm kind of skipping a step of showing everything after I distribute. I hope that's okay with everyone. And then the minus sine beta sine pi over 4 with a negative sine beta sine pi over 4 after you distribute the negative means I have two of them, but negatively. So now I have negative 2 times the sine of beta times the sine of pi over 4, which still equals 1. Here you could divide by negative 2 first, or the sine of pi over 4, you could evaluate that. I think that's what I'm going to do first. So negative 2 sine of beta, sine of pi over 4 is root 2 over 2 from our unit circle. And now that 2 in front can cancel with the dividing by 2 on the bottom. That root 2 that's left, I'm going to move in front of the sign. So now I have a negative root 2 times that sine of beta, still equal to 1. Now I want to isolate the sign, so I divide both sides by negative root 2. So sine of beta should equal a negative 1 over root 2. Rationalizing the denominator means multiplying top and bottom by root 2, which gives us the sine of beta is negative root 2 over 2. That's a special evaluation on our unit circle. So I would consider the circle now. I wasn't given an interval over which to solve, which means this is the kind of problem that's an infinite solution set problem. So visualizing our circle, our sign will be negative in quadrants 3 and 4, where y is negative. And at the pi over 4 angles, that's where our y value is negative root 2 over 2. Who cares what x is here, since we're dealing with sine? And here, notice there is no common difference. To get from 5 pi over 4's location to 7 pi over 4's location, that would be adding pi over 2. But then to get from that quadrant 4 answer all the way back around to quadrant 3, that would be adding 3 pi over 2. And since those two angles are not the same, we have no common difference. Which means when I go to write my answers, I'm going to have two different boxes worth of an answer. So I'm going to have that beta equals this quadrant 3 location. I'm going to use 5 pi over 4, but any angle that lands there would be fine. Plus, getting back to quadrant 3 means going a whole circle around, or 2 whole circles around, or 3 whole circles around, or going backwards by those whole circles. So this means I'm adding integer multiples of pi, so k pi, where k is in the set of integers. This takes care of the quadrant 3 answers. Similarly, if we want the quadrant 4 answers, I'm going to use 7 pi over 4 plus k pi, where k is in the set of integers. Questions here?
So are we using like the general rule about which quadrants it can be in? Wait, never mind, because it has to be in the negative things. Never mind. Thanks.
Yep. Okay. Double angle formulas. This was the week when a lot of you were getting really close answers, but people's signs, SIGN, meaning positive and negative, were wrong in a lot of cases. And I was having to fix all of your signs in places. So maybe this one is more important than the others to talk about again, because that's really important and was making a lot of answers wrong. So here, cosecant is negative 8 over 3. I'm going to recall for myself that cosecant, if I had a labeled diagram the way we've studied it, cosecant would be r over y equals negative 8 over 3. So I'm going to put that negative 8 over 3. And we're given an interval of 3 pi over 2 to 2 pi. So that means I'm in quadrant 4. So I'll just note that for myself. And in quadrant 4, for x and y, our x is positive, but our y is negative. which means here for r over y, that y value that I'm going to use of 3, I'm going to make a -3. So here, I need the missing information, which is the x value. So I'm just going to make myself a right triangle. Doesn't matter what it looks like. But since I'm using a diagram, and I'm going to use Pythagorean Theorem, you definitely need the right angle box, and you definitely need to label where theta is. Doesn't matter where you put it, as long as the trigonometry you use is correct based on where that location was. So here, if I put theta right here, my opposite y would be across from it, my adjacent x would be next to it, and my radius of the circle would be the hypotenuse of the triangle. If you labeled theta up top instead of where I put it, your x and y would just have to swap places. So here I'm going to say that y is a -3. I'm going to say my radius is a +8, so that now the cosecant would be defined as 8 over -3, which is what we were given in the problem. And the x now I'm going to solve using Pythagorean Theorem, which I can only use if it was a right triangle. So when you guys drew your diagrams without the right angle box, I circled it, kind of pointing out that that was really important that you had. So if you don't use a diagram, you're fine. If you use a diagram, you really need to put that right angle in the picture. So now x squared plus y squared should give us r squared. So x I don't know, that stays the way it is. Y is a -3, which gets squared, and r is an 8, which gets squared. Notice I put the -3 in parentheses, but not the 8. The -3, if you didn't have in parentheses, you'd be reflecting the math incorrectly. So make sure with a negative that's getting squared, you always put that in parentheses. -3 when you square it would be a +9, and 8 squared is 64. Subtracting that 9 means that x squared equals 55. And then square rooting both sides gives x equals square root of 55. 55 is 5 times 11. Those are the only factors other than 1. And root 5 doesn't simplify. Root 11 doesn't simplify. So that's just going to have to stay the way it is. And in quadrant 4, where my problem dictates my angle is, my x value stays positive, so that's going to stay positive. So I'm just going to note here, positive x in quadrant 4. If we were in a negative quadrant for x, that's when I'd turn that into a negative root 55. So now, using double angle formulas, sine of 2 theta, the formula says, is 2 times the sine of theta times the cosine of theta. So replacing that stuff, that's 2 times. Sine is y over r. So according to my picture, my y is -3, my r is 8. But that's just the reciprocal of cosecant, so it should make sense that I got the reciprocal of -8/3. Cosine is x over r. We found our x value to be root 55. And our r value is still an 8. This is the point where some people were putting negatives and positives in the wrong places. So this is the thing where you just be careful. I know this is positive root 55 over 8 because I'm in quadrant 4. And I knew this is -3 over 8 because I'm in quadrant 4 where y is negative. Now I don't have to worry about the end results being positive or negative because I'm just doing the math that's written on the page now. So a positive times a negative times a positive definitely means my final answer is going to be negative. 2 times 3 is 6, times root 55 is 6 root 55. And in my denominator, the 1 underneath the 2 times 8 is a 64. And now all I'm going to do is reduce the fraction because 6 and 64 both can be divisible by 2. So that leaves me with -3 root 55 over 32. I can't reduce anymore because 3 doesn't go into 32. So this is my final answer for sine 2 theta. Cosine 2 theta, the formula for that from your notes is cosine squared of theta minus sine squared of theta. Here, this is where a lot of you on the homework from that week were switching them around. Cosine, we found, is the root 55 over 8, so that has to go in front, minus the sine, sorry, that gets getting squared, And sine is the -3/8, which has to get squared. So again, that's where some of you had them reversed. And so if the answer was something like -1/9, a lot of you were giving me a +1/9 because you had those backwards. So just be careful there when you do similar problems. Squaring here gives me 55/64 for the first fraction, minus squaring that negative gives me a +9/64. And then 55 minus that 9 gives me a 46/64. Here I can divide by 2, giving me 23/32. 23 is prime and isn't a factor of 32, so I know that's my final answer for cosine 2 theta. And then finally, tangent 2 theta. Some of you on the work were doing all of the work all over again, but don't forget, tangent is just the sine of 2 theta over the cosine of 2 theta, which we had just taken the time to find. So you don't need to do all the work all over again. You're just going to put your answers that you already got. So sine was -3√55/32. Cosine was 23/32. Those denominators are the same, so I can shortcut divide those out. And that leaves me with -3√55/23. And 3 doesn't go into 23, so that's my final answer for tangent 2 theta. Questions there? Are you guys still there also? Can someone shout at me so I know you're still there? Okay. Awesome.
Yep.
So again, some of you were kind of looking at the final answers and using that point to decide, should they be negative or positive? That was the wrong move. You determine whether the earlier things were negative and positive when you swapped into the formulas to begin with. Then you're just doing the math, and whatever you get is whatever you get. Okay, so just be careful there. So that was reviewing double angles. And then finally, we come to the last 2 weeks, which are the most freshly in your mind probably. So here, solving for that x value in this diagram where I have 3 sides of a triangle. This is where, now that we are doing both of them together and not in isolated weeks, knowing your cases helps. So I have the side, side, side case, which tells me I need to use the law of cosines. And I'm looking for x, which is opposite 7. So I'm going to use the formula where I start with that 7 and end with the cosine of that angle x. So by law of cosines, I have 7 squared has to equal the sum of the other 2 sides squared, 13 squared plus 12 squared, minus 2 times those other 2 sides times the cosine of that angle x. Now I'm just simplifying. 7 squared is 49. 13 squared is 169. 12 squared is 144. 13 and 12 is 144 plus 12 is 156. Did I do that right? And 156 times the 2 is 312, I think. Someone catch me on that if I did my mental math wrong. Here I can combine like terms, so 169 and 144 can come together, giving me 313. Again, someone catch me if I did something wrong. Minus that 312 cosine of x. Don't forget, we cannot subtract 313 and 312 because that 312 is glued to the cosine using multiplication. But we can subtract 313 to the other side. So here it looks like I get a -2, 6, 4. Does that look okay?
Yep.
Still equal to negative 312 cosine of x degrees. Now I would divide both sides by negative 312. So negative divided by negative cancels those negatives. So 264 divided by 312 would equal cosine of x. And to get x, I just have to take inverse cosine of both sides. Some of you are putting the inverse cosine at the back. Don't forget, it's not multiplication. It has to go in front. So inverse cosine of both sides cancels cosine on the right, leaving me with x degrees, or the measurement of angle x. And now, calculator is allowed here for this kind of problem. So I'm going to pull up calculator. Make sure you're in the right mode. This kind of calculator is already in degrees. So 264 divided by 312, taking the inverse cosine of that result, gives me this 32-degree answer. Switching to approximately, adding my degree symbol, and here we're being asked to round to the nearest hundredths place. Some of you are still rounding incorrectly, which is really frustrating for me. It'd be nice if you guys could pay better attention to how you're rounding. And I'm not docking people because it's silly for me to dock you when you had the right answer, but it was rounded wrong. But it's also really annoying to see seniors and juniors rounding incorrectly. Now, obviously, I'm not going to dock you because you're not going to resubmit a homework just to round correctly, but still, come on. So hundredths place means tenths place is the 2, hundredths place is the 0. So looking behind the 0, that 4 doesn't round the 0 up at all. So it looks like my x equals 32.20. I'm asked for the hundredths place, so I should show the 0. I don't need degree symbols because the degree was on the x in the first place. I'm just solving for x here. Questions here? We only have one more problem, and then I'll take attendance real quick, and then people can keep out. Question?
No.
So that was reviewing law of cosines. This last one should be reviewing law of sines. Then we'll be done. So let's get this out of the way. Triangle ABC. You may not need a picture. I'm just going to make a picture for myself. Picture is not going to be to scale, obviously. I'm just making any triangle that I want. Going to label the angles ABC. Measure of angle C is 40 degrees. Label that. Measure of angle A is 80 degrees. Segment BC is 12 centimeters. And segment AC is 10 centimeters. We're looking for segment AB. So if you want, you could put a variable there. I'll just put an X. Otherwise, you could just leave it AB, or measurement of segment AB. So I'm looking for X. So here, what I was given was an angle, a side, and an angle, and then another side technically. But if I just focus on the things that are opposites, X is opposite 40. 10 would be opposite angle B, but I wasn't given that, so that's not going to be helpful. 80 degrees is opposite 12, so that will be helpful. So here I know that according to the law of sines, the sine of angle A, which is 80 degrees, divided by its opposite side length, which would be little a if you were writing it out with the rules, but here I'm just straight plugging in. So over 12, that should equal the sine of angle C, which is 40 degrees, divided by the opposite segment of measurement of segment AB, which I labeled with an X. You didn't have to do that. So here, cross multiplying gives X times the sine of 80 degrees equals 12 times the sine of 40 degrees. Dividing to get rid of sine of 80 on both sides gives X equals 12 sine of 40 degrees over sine of 80 degrees. And again, just as a note, a lot of you are not putting your degree symbols in your work, and I'm having to do it for you. Again, not something I'm really docking for, but you know, otherwise it means radians. So if it was a quiz or something, you definitely lose a lot of points. So now I'm just using my calculator. So doing my denominator first. I think we established the last time I didn't really need to do this first, but I'm so used to doing that. I'm going to store that in memory with m plus. Numerator, 40 with the sign times that 12 divided by that thing I stored in memory equals 7.8 and change. Is approximately x. X is a segment length, so no degrees needed here. I'm just going to do that again in the calculator without doing the denominator first, just to show that I think we were safe. So if I did sine of 40 first, then times the 12 equals dividing by 80, and then take sine, then equals, same number. So I didn't have to be ultra conservative there with the order of operations with this calculator. So now, rounding to the nearest hundredths place, please read directions. Hundredths place again means that I'm looking at that 2, which is in the thousandths place. 2 doesn't round the 3 up. So this is, x is approximately 7.83. I need units, and the units I was given for the segment lengths are centimeters. So don't anyone leave because I want to take attendance, but I just covered every topic that we've done since we left school, starting with the proofs stuff, working into sum and difference formulas, double angle formulas, law of sines, law of cosines. So again, you can look at any of those previous notes as well as the formula page that I shared with you guys, and it's on Canvas, not what I wanted to do. So this formula page has everything you should need. But again, you can look at any of those PDFs of past notes when we did isolated weeks of the topics. Okay, so you can use that. Let me stop the recording and then let me take attendance. I'm hoping that recording works.